Okay.
Okay.
So our second speaker this morning is Antoine Bourget from École Normale Supérieure in Paris and the PhD in Saclay, telling us about magnetic quivers for symplectic singularities.
Thank you. Well, thank you everyone for coming here, and thanks for the organizers for inviting me. And I guess I should also thank my collaborators. Some of them are listed here. All the results presented here are done in collaboration with some of them over the past 3 or 4 years now. So I will be talking about magnetic quivers and symplectic singularities. So I don't expect that you know what any of these two concepts are. So I will explain this. But first, let's start with some motivation. And the motivation will be examples to tell you that actually these symplectic singularities are a relatively common thing in math and physics. So let's start with some mathematical motivation with a list of examples. So some examples of symplectic singularities are the standard Kleinian singularities, C2 mod gamma, where gamma is a finite subgroup of SU2. So these surfaces are in the class of symplectic singularities. Another very vast class comes from hyperKahler geometry. If you take any hyperKahler quotient of some vector space by some reductive Lie group, well, you will end up with symplectic singularity. Another big class from representation theory is closures of nilpotent orbits and also transverse slices in affine Grassmannians, and I will illustrate how some of those arise. And then from a more physical perspective, Higgs branches of a very large class of supersymmetry gauge theories are in this class, and also 3D n equal 4 Coulomb branches. And all of this will be useful. So the goal of this talk is to define a combinatorial tool, the magnetic quiver, which allows to define and completely specify a symplectic singularity. And then I will explain what we can know from the knowledge of such a quiver. And in particular, we will know the structure of the coordinate ring and the structure of the singular stratification. So I will explain all this on examples. And of course, I also need to tell you how one can compute such a magnetic quiver in the first place. So the physical motivation, and this is where I come from, is from Higgs branches of theories. So more concretely, the Higgs branch of theories with 8 supercharges is in this class, as I said in the previous slide. And therefore, this can be used as a kind of shortcut to explore the landscape of supersymmetric theories. And so one big question in particular is, what is the landscape of superconformal field theories with 8 supercharges? This can be done in any dimension, say for concreteness from 3 to 6. And this is a very hard problem. And okay, a slightly simpler problem is to explore what is the landscape of these singularities, because to any theory, one can associate such a singularity. So if we know how to classify or explore these things, this gives a coarse version of the exploration of this. And so we'll see that the magnetic quiver is useful in that. So the plan of the talk is very simple. I will explain what are magnetic quivers, what they are useful for, and finally, how we can construct them. And as you can see in this plan, it will be based on many examples. So along the talk, I will introduce several examples to illustrate. So let's start with what it is. So the general idea is just that symplectic singularities are the singular version of hyperKahler manifolds. If you're more used to Gorenstein singularities in Calabi-Yau, this is exactly the same. Symplectic singularity is to a hyperKahler manifold what the Gorenstein singularity is to a Calabi-Yau manifold. The formal definition was given by Beauville about 2 decades ago and goes as follows. So if you take a complex algebraic variety X, then it's a symplectic variety if it's normal, and if its smooth part has a symplectic form, which can be extended to a holomorphic 2 form on any resolution of that variety. So this is a very general definition. I will not use too much the details of this. And also I will restrict on a slightly narrower class, which are the conical symplectic singularities, where in addition, I demand a grading, well, a C star action, which corresponds to a grading of the coordinate ring, a grading by the integers. And the fact that it's conical means that the zeroth part is just trivial, it's just one dimension. And the fact that it's compatible with the symplectic structure means that the symplectic form has a given weight, which I take to be -2. And this is important because then it means that the -2 part here, the n equal 2 part here closes and forms a Lie algebra, which is the global symmetry of the space. So as I said, this occurs in supersymmetric theories. And here I will focus on superconformal field theories in dimensions 3 to 6. So due to a famous theorem of NAM, so 6 is the maximal dimension. And the character of superconformal theories in all those dimensions varies a lot according to the dimension. In high dimension, 5 and 6, typically the SCFTs are rare. They are isolated, and one way to see this from the superconformal algebra is that they rely on these exceptional isomorphisms. And in particular, they will never be Lagrangian. You cannot write a Lagrangian to define such a theory. This is different in 4D, where it's much more broad. You can use Lagrangians, but you can also use other constructions. There is a very large class of class S theories, Argyros-Douglas theories, etc. And then in 3D, it's even larger in a way. And a very large class is quiver gauge theories, or rather the infrared limit of such theories. So I will illustrate this. So one important point, and the reason why the Higgs branches is in the class of symplectic singularities, is because of the presence of these SU2H factors that are here in blue in the bosonic part of the bosonic subalgebra of the superconformal algebra. And the other thing that you can observe is that in 3D, and only in 3D, there is another SU2 factor in this bosonic subalgebra. And this tells you that there is another branch of vacua, the Coulomb branch, which is also a conic symplectic singularity. And this plays a fundamental role in this story. Actually, this is the central character of this story. So let's give the definition. This is the main slide. What is magnetic quiver? So as we just saw, the Coulomb branch of a 3D n equal 4 superconformal field theory is a conical symplectic singularity. And it's not an easy space to define. As opposed to the Higgs branch in the Lagrangian case, where it's just a hyperKahler quotient, the Coulomb branch is very involved. It involves this dressed monopole operators, which become massless in the deep IR. So it was a very long story to define this, even in physics, but a big step was achieved in around 2009 by Gayotto and Witten, and then in the following years by Cremonesi, Hanani, Zaffaroni, and Bullimore, Dimov, Gayotto. They gave different approaches to understand the Coulomb branch. And roughly at the same time, Nakajima, and then with Braverman and Finkelberg, provided a very rigorous mathematical definition of these Coulomb branches. So now all of this really belongs to the field of mathematics, and it's all very well defined. And it allows me to make this definition. So the concept of good quiver is just, so I will show examples later, but there is some constraint on the ranks of and flavor content of the various gauge groups that I will show later. But if you take a good quiver, one can define a 3D n equal 4 SCFT. So this, so when you take a quiver, there are vertices and links. The vertices are the gauge groups. The links are the hypermultiplets. And the fact that it's a good quiver allows you to have a well-defined limit in the infrared. So you have an interacting conformal field theory of which you can take the Coulomb branch here. You take the Coulomb branch, and then it defines for you a conical symplectic singularity. And for the purpose of this talk, I will need a slightly more general notion of quiver. So that's why I call it generalized quiver, but let's forget about this for a minute. So this whole thing can be summarized in this map C, which is the Coulomb branch. We will call it the Coulomb branch for short, but it's really all this process that you should do. And a magnetic quiver is just an inverse for that. So if you have a symplectic singularity X, a magnetic quiver for that is a quiver such that C of Q is X. So yeah, I will show example. Oh, no, not this way. So let me give very, very simple examples. The simple class is closures of minimal nilpotent orbits. So first, I need to introduce my notation. So this is the first quiver we see. So let me spend a few minutes on describing what I mean by such a graph. You might complain that this is not even a quiver because there are no arrows. So actually what I mean with this graph is actually what's on the right here. So this is sometimes known as a double quiver or double frame quiver or triple quiver sometimes. So anyway, the main point is that this means that. So you can see there are several differences. So every edge here, which is non-oriented, actually stands for 2 arrows in opposite directions. Also, on every circle, which represent physically the gauge groups, there should be a self arrow like this. And you can see that there is also a framing here, which is not present here. This can be seen physically as the engaging of a diagonal U1 gauge group in this theory, which is a product of unitary groups. And mathematically, this is known as the Crowley-Bovee trick in the representation theory of quivers. So because this is much easier to draw than that, I will always use that kind of drawing. So now the first fact, once you have this notation in hand, the first fact is that affine Dynkin diagrams are magnetic quivers for closures of minimal nilpotent orbits. So here's an example, the quiver here. The Coulomb branch of this is the closure of the minimal nilpotent orbit of SL4. So just to remind you what a nilpotent orbit is, you just take a nilpotent element in the algebra, and then you take its orbit under the adjoint action of the group. And for short, I will denote this minimal nilpotent orbit with like this, with a lowercase letter with an index. So this, if it's A3, it means that it's the minimal nilpotent orbit of the algebra A3. And okay, so this is a well-known fact. And so here are more examples, but already we see that there are some problems. So here, okay, no problem. E6, you just take the affine Dynkin diagram of E6 and you generate this way the minimal nilpotent orbit. But then let's take a non-simply laced algebra like F4. Then what's happening here? You need to introduce a non-simply laced edge. And that's why I needed to introduce the concept of generalized quiver, because this you cannot really translate using this. You cannot really use this. It's not well defined. So I have to define what I mean by this arrow. And well, the definition is as follows. If I have a non-simply laced quiver, so here is another example of a non-simply laced quiver, you can always unfold it. So then you get a quiver like here on the right. And then you can take the Coulomb branch of that one. And there is, so if it's a double arrow, you have a Z2 action on that space, and then you take the fixed points. So this is by definition. And so this has been intuited in physics almost 10 years ago, and more recently Nakajima and Weeks formalized this notion. So now the Coulomb branch of those kind of generalized quivers is also in the realm of well-defined mathematical things. Another remark, yes, you might be worrying about this black dot over here. It's just the nodes which are not balanced. So the sum of the neighbors of this node is not equal to twice the value of that node. And this is important because if you look at the remaining part of the quiver, the white dots, they always form a union of finite Dynkin diagrams. And this is related to the global symmetry of the symplectic singularity. Actually, this is one of the first uses of these magnetic quivers. So in this previous slide, we now know how this is defined. You just unfold. So if you unfold this, you get actually this. And so this tells you that the minimal nilpotent orbit of F4 should be some kind of fixed point in that of E6. And actually, this fact was observed by Kostant and Brzezinski long ago. So this is all compatible. And finally, I should also insist that there is non-unicity of magnetic quivers. As you can see here, E6 can be represented in at least 2 ways, actually in many more ways. Okay, so this was a class of examples, nothing new here. This was actually one of the constraints that Nakajima had on his construction to reproduce this. Now let's move to physics and to have some more non-trivial examples. And the examples I pick are 4D n equal to SCFTs. The question is, how do you characterize such a CFT? You can construct it in many ways. I mentioned some of them, class S, you can have some brain system, you can just take a Lagrangian, you can specify a certain point in moduli space of other theories, like how Argyros-Douglas theories are defined. But you'd never know if this is there is never only one way to define a theory that way. And maybe there are two inequivalent ways to define the same theory. So how do you give characteristics of a certain theory? Well, a list of characteristics which are well defined are the flavor symmetry, various central charges, the geometry of the moduli space of vacua, the Coulomb branch, the Higgs branch, and then more complicated things like the Seiberg-Witten curve, the integrable system associated to it, the spectrum of VPS states, some various classes of indices, starting with a superconformal index, the 2D VOA that is obtained after some cohomology is taken, etc. So there are a lot of things. I will focus here on the moduli space of vacua, because as you understood, the Higgs branch can be characterized by the magnetic quiver. So let me say a few words about that. This can be used to do some kind of bottom-up exploration of the landscape of SCFTs. So I will give you an example in the simplest case, which is the rank 1, when the Coulomb branch has the smallest possible dimension, which is one complex dimension. Then the low energy physics is governed by the singularity. Because it's one-dimensional, there is not much you can do. It's conformal, so it has to be some kind of cone with a point here where the theory is strongly interacting. And then on the generic point on the Coulomb branch, you just have some abelian gauge theory. And analyzing the singularity here, you can understand, you can define what is the SCFT. Actually, you need a bit more. You need to specify what is the singularity, which will be part of the because there is an elliptic fibration over this, it's part of the Kodaira classification of singular elliptic fibers. And you also need to explain how this can be deformed under mass deformations. But in a beautiful series of papers, Philippe Argyros, Lotito, Lu, and Martone obtained this list, this constrained list of possible geometries of rank 1 SCFTs. And this is a finite list, so that's the list. And actually, all these theories have been constructed explicitly. So there is actually a perfect match between the bottom-up approach of constraints and the top-down realization in string theory. And most of these theories are non-Lagrangian, actually. So, this result is pretty non-trivial. And so it's specified by the Kodaira class of the singularity and how it can be deformed. So I don't want to spend too much time on this because this is Coulomb branch computation, and I remind you that Coulomb branch in 4D are not in the class that I want to study. They are not symplectic singularities. But the point is precisely that I would like to get the same result from the Higgs branch perspective. So to give an example, I picked one randomly. So I picked this one here, the first in this category here, the C5 theory. And just to illustrate what I said in the previous slide, how can we characterize this thing? We can compute the flavor symmetry, the level, various central charges. The Coulomb branch geometry is characterized by what I just showed in the previous slide. You can compute the spectrum of BPS states as a BPS quiver. And this was actually published recently, a few months ago, by Michele Del Zotto and Iñaki Garcia Echevarria. You can compute superconformal indices based on some class S realization. But what I'm interested in here is the Higgs branch geometry. And this is pretty difficult because, as I said, it's not a Lagrangian theory, so you cannot use hyperKahler quotient. What was known before is the dimension, which can be computed from the central charges. So it's known that it's a space of quaternionic dimension 16, so complex dimension 32. So you see that while the Coulomb branch is very simple, one-dimensional, the Higgs branch is 32-dimensional. So how can you characterize it? Well, my claim is that you can characterize it using a magnetic quiver, and here it is. So I will tell you later how we can compute this and what we can extract from this. But what I want to emphasize here is that this quiver contains the full information about that Higgs branch. And as far as I know, it's one of the only ways to characterize this. Actually, there is another way using the VOA and associated variety, using the 4D 2D correspondent. But from this, we can extract data in a very algorithmic way that I will show next. So, okay, this is just an example, and we were able to do this for all these rank 1 theories, so that is a complete list. And okay, this is the result. So here I didn't show the result because it was known before that the Higgs branch of those first maybe 8 theories or 7 theories are closures of minimal nilpotent orbits. So the magnetic quivers are affine linking diagrams, as I showed previously. But then for all the others, you need these folded quivers. Okay, so this is to tell you that we can be pretty explicit and compute in a large array of cases. But now, what is this useful for? What do we do with that? So that's the second part. What does this tell us? So the general idea is that if you have a symplectic singularity, you can, in principle, extract things from it. Like you want to compute the Hilbert series, which is the graded dimension of the coordinate ring, graded by the grading I introduced at the beginning. Or what is very interesting is the stratification into singular loci. And what I claim is that if you know a magnetic quiver for this, so you know this part, then you can bypass this complicated computation, and you can directly, with a very simple algorithm, very explicit formulas, you can obtain this data about the singularity. So I think in the interest of time, I will maybe skip. So I wanted to describe these two things. So, well, okay, I will say very briefly some words about the Hilbert series. So this messy slide is just to introduce notations, but pretty straightforward. The fact that we have a set of vertices, a set of edges, etc. And the bottom line is that you have a very explicit formula, which is shown here at the bottom. So you have to introduce all these notations, but this is based on the realization of the Coulomb branch as addressed monopole operators, and you obtain this formula, which tells you the graded dimension here of the symplectic singularities purely in terms of quiver data. This delta here is this formula which involves only the edges and the nodes, and well, everything is completely fixed by the quiver. So this formula can be used in particular to extract the dimension, and actually if you refine using fugacities for the global symmetry, you can extract the C2 part, the C of X2 part, which is, as I said, the Lie algebra of the global symmetry. So you can extract the exact global symmetry. So, and you can do this for the particular theories that we were looking at before, this C5 theory. So if you brute force evaluate that formula, well, you get a result like this, which is not so illuminating, but it's explicit. And from that, you can then, using the refined version, you can extract the spectrum, so the generators and relation that define the Kahler ring. And it's not a complete intersection, so it will go on forever, but you can extract this using the platistic logarithm. And in particular, at order t squared, you see here the adjoint representation of SP5, which tells you that indeed the symmetry is SP5. And if you want to know what is the global form of that symmetry, you can also look at which representations appear. And you can do this generically using what's called the highest weight generating function. And it tells you that the symmetry is really SP5 and not a quotient of SP5, for instance. So I went a bit fast on this, but because the main point I want to make is the other thing you can compute, which is this stratification. So what's this about? The point is, any conical symplectic singularity has a finite canonical stratification where so this is your singularity, it starts with x0, and then you have lower dimensional sub-loci. The closure, sorry, each of these xi is the singular part of the xi minus 1. And each the closure of each, the normalization of each is again a symplectic singularity. And then you have a notion of transverse slice. You can see how one is embedded in the next. And this stratification defines a partial order given by this inclusion. And we can represent this partial order with a Hasse diagram. So here is a picture. So here is this Hasse diagram. And here is what it means geometrically. So we still have our 32-dimensional Higgs branch, very complicated. But with this diagram, we can really understand. We can break it into elementary bits. So this is E6, our nilpotent orbit from the beginning, and C5, same minimal nilpotent orbit. And what this tells you is that you have a singular point. This is the tip of the cone in red here. And then you have this C5. So this is a 10-dimensional space, which I represented by this blue line here. And then you have, on top of this, you have an E6 minimal singularity, which is 22-dimensional, which emerges from there. And this whole thing generates this 32-dimensional big Higgs branch. So as you see, secretly, it was actually made out of 2 bits, a C5 and an E6. And physically, this is very interesting because it corresponds to Higgsing or generalized Higgsing. So that theory that we started from can be Higgsed if you move on the Higgs branch, if you move to not the generic point in the 32-dimensional thing, but on this blue 10-dimensional thing. If you move here, then you have partially Higgsed the theory and you have moved from the C5 to the E6 in the list that I showed at the beginning. So this is a very simple example, but this is completely general. You have always such a stratification, and this physically corresponds to Higgsing. And now the claim is that this is very difficult to compute in general, but if you have a magnetic quiver, it's completely straightforward using something called quiver subtraction. So I won't have time to explain the details of this algorithm, but the idea is quite simple. What you need is 2 things. You need the quiver you start from, obviously, and you need a list of elementary symplectic singularities with a corresponding magnetic quiver that you can subtract. And this list, for the algorithm to work, this list needs to contain all the elementary slice which will appear in the singularity you start from. And I will come back to how we get this list. But once we have this list, then it's simple. You start from the quiver here, and you scan through that list. Which quiver can I embed in there? And for instance, well, in this list, we have the E6, and we saw before that this is a quiver for the E6. So then you can subtract it. So you see that this can be embedded in this, and then there is a process of subtraction. And well, if you do this, you obtain that one here. And then here you obtain the affine diagram of C5, and then you can subtract it, and then you get nothing. So this is how you obtain this from quiver subtraction. So as you see, a main part is, of course, to have this list. So, and I will come back to this. Before that, let me just mention that using this technique, you can obtain the stratification of the Higgs branch, and combined with other techniques coming from Coulomb branch geometry, you can obtain the full map of the moduli space of vacua, of supersymmetric vacua for this kind of theories. And for our example here, it is this space where you have the Higgs branch here, and this is the diagram we just saw before, which is hyperKahler. And then you have the Coulomb branch parts. And so the Coulomb branch is here is 1-dimensional, and it has this 2-star Kodaira type singularity. And then you have also here an enhanced Coulomb branch and, well, various other structures. So we can completely map out, and these are the phases of the theory. So this is the phase diagram, if you want, of the theory. So for this to work, we need this list. So here is such a list. I don't know if it's, yeah, it is readable. It's, if you want, it's the list of atoms of symplectic singularities. Each of them are the elementary blocks, and then you can construct any other symplectic singularity by combining these atoms. Of course, this is true only if this list is complete. So is it complete? Well, the answer is no, it's not complete, and it's probably far from complete, and it is a very big open problem to complete this list. However, it's already pretty good, and I will explain how this particular list comes from. And this already covers a very large class of at least physically and mathematically interesting spaces. So where this comes from is from slices in affine Grassmannians. So affine Grassmannians are infinite dimensional spaces, which are defined from from a Lie group. So here I will take some compact Lie group. Think of SLN. It's an infinite dimensional space, technically some in scheme. The interesting bit for us is that there are actions of a certain group, of the group G of T here, acts on this, and there are orbits which are labeled by dominant co-weights of the starting group G. And these dominant co-weights, they are partially ordered. We say that one is lower than the other if the difference is a positive integer combination of co-roots. And then the slice between any two orbits labeled by two co-weights like this is a finite dimensional slice of dimension given by this, where rho is the Weyl vector. And if lambda and mu are adjacent, so they are right next to each other in this partial order, so they differ by a co-root, then this is an elementary conical symplectic singularity. So by scanning through all affine Grassmannians of all simple Lie groups G and looking at all possible transverse slices like this, we have already a big list, and that's where that list came from. So I will just illustrate this with some simple examples. This is the vanilla case. This is SL3. So you have slices. So okay, this is the Weyl chamber. This is the fundamental Weyl chamber, where the fundamental weights would be here and here. And this is the highest co-root. And then here you move along simple co-roots. And when you move along simple co-roots, the slices are these AN, this Klein singularity C2 mod ZN. And here, and only here, you don't have enough space in the fundamental chamber to move along a simple co-root. So you have to move along another co-root, and then it gives you the minimal nilpotent orbit here, the lowercase a2. So, okay, maybe you notice that here not all the co-weights are represented. It's because they are disconnected parts in the affine Grassmannian, and the other parts, the co-weights which are non-co-roots, would be this. And well, there are no big news here, only Klein singularities. And for each of those slices, there is a very simple formula given by, in particular, Braverman, Finkelberg, and Nakajima, which tell you basically what is the magnetic quiver. Now, it's more interesting in cases where the Weyl chamber is more narrow. So here is the example of G2, which is the most interesting example that I can draw in 2D. It has to be rank 2. So the Weyl chamber is much more acute like this. And you can see that on the top part, not much is happening. You can move along dominant co-roots. So you again get these Klein singularities. At the very bottom here, you have the minimal nilpotent orbit of G2. It is all fine. But then there is an intermediate regime over here where you can move not along simple co-roots, but not along the highest either. You are kind of in between because of the shape of this chamber. And it gives you these weird things called AC2 and AG2. These are called quasi-minimal singularities, and they were identified by Malkin, Ostrich, and Vibornov 20 years ago. And we can compute magnetic quivers for them. We can analyze these slices using the techniques I presented. And these are important additions to our list. And maybe surprisingly, you can think, oh, this is very exotic and we'll never use that in physics. But actually, no. As soon as you are in rank 2, SCFTs in 4D, for instance, they already appear as transverse slices. So if we missed that, then we wouldn't be able to understand those Higgs branches. So they are actually very omnipresent, and they appear completely generically. So I think I have 10 minutes. So, okay, so in the last part, I have to tell you how we derive those things. And there is a host of methods. I will obviously not review all of this. Here are a small subset of papers which derive magnetic quivers in one way or another. Most of them use some kind of string construction or geometric engineering. It's also deeply related to 3D mirror symmetry. Okay, so I can't describe all of this, and I will focus on one particular method, which is 5D SCFTs. And 5D SCFTs realized and the link with toric geometry. So 5D SCFTs, well, they were discussed actually yesterday in Hyun's talk, so I don't have to introduce too much. They are very interesting from the physical perspective and from the Higgs branch perspective because they are non-Lagrangian. So it's a big problem. How do you describe the Higgs branch of such theories? So for this, okay, how do we construct this in the first place? There are several methods. The two that I will use are the first two bullet points here. So this is a very long story, starting with Seiberg in the almost 30 years ago, but many, many authors contributed to this story. I cited only a few of them here. The construction I will use are M theory and a canonical threefold singularity, and as the world volume of brane webs in type 2b string theory. So the notation here is that these are brane webs. The horizontal segments are D5 branes, vertical as NS5, and these dots, these circles are 7 branes on which 5 branes can end. Now, the idea of this construction is as follows. We start from a toric polygon. A toric polygon is, we saw many of them in previous talks. It's just a polygon, a convex polygon with vertices which have integer coefficients in 2 dimensions. From this, as is well known, you can define the toric variety associated to this, which is a local Calabi-Yau threefold. And then if you put M theory on that threefold, well, at the tip of the singularity, you have a 5D SCFT, of which you can take the Higgs branch, which is a symplectic singularity. So this is the object we want to study. And this is the standard construction for it. Now, what I claim is that there is a direct algorithm which takes as an input the toric polygon and outputs a magnetic quiver, which is directly the magnetic quiver for that singularity. And that allows to study it in a completely straightforward way. And so this was done by Cabrera, Hanani, and Yagi 4 years ago. And it can be reformulated as a decomposition into Minkowski summons of the polygon. And with Marike van Best and Sakura, Stefanemeki, and Julius Eckert, we actually put out a Mathematica code, which you can download on the archive submission, where you just input the coordinates of the vertices and it outputs the magnetic quiver. It's completely straightforward. Let me give an example of this, and I will illustrate with how this is computed. So if I start from this simple toric diagram, it's well known that the threefold associated to it is the conifold, and the 5D theory that you generate is the E1 theory of Seiberg, which is a completion of pure SU2. And the Higgs branch is C2 mod Z2. It's generated by massless instantons. Now, the algorithm going the other way is very simple. You take the toric polygon, you dualize it, so you obtain this that you interpret as a brane web. So this is a 1-1 brane and a 1-1 brane. And then you compute, you see these branes as tropical curves. And well, here it's a bit trivial because they are just straight lines, but in general, they are tropical curves because of charge conservation. And there is a notion of tropical curve intersection, stable intersection. And then you just put 1 dot for every brane, and you connect them with as many links as this tropical intersection. So this gives you this graph. And this you interpret as magnetic quiver. And here you find affine A1, and it's well known that the closure of the minimal nilpotent orbit of A1 is C2 mod Z2, so the graph commutes. So this is a shortcut to define the Higgs branch. Okay, this example is a bit trivial. Let's look at a less trivial one. If we take SU3 with 6 flavors as a gauge theory in 5D, there is a UV theory whose deformation is that. And okay, it's known that the toric polygon you have to start from is this. And using a similar process with the dual brane web, which is here, and then collapsing it to reach the superconformal points, you obtain this diagram, and then you read the various intersections of all these branes, and it gives you that quiver over here. You can also compute what is the threefold. It's given by those equations. But of course, once you have those equations, it's very non-trivial to find, okay, what is the 5D theory and how to characterize it? Even what is the dimension of the Higgs branch? Even this is hard. What I claim is that, okay, you can use quiver subtraction on this, and you obtain this Hasse diagram here. You see that there is a branching because there are, if you scan through all the things you can subtract from here, you see that there is a D5 affine diagram, which is embedded here, but there are also 2 E6 affine diagrams. So that's why you have these 3 branches. So it's very complicated stratification, but very easy to derive. And what we deduce from this is, okay, this structure. And it's very different from this, what I put here is the symplectic quotient, the hyperKahler quotient that you would think, the naive Higgs branch there. And the difference between those two things, they tell you about what is non-trivial about 5D SCFT Higgs branches. For instance, the dimension has jumped. If you compute dimension here on the right, it would be 20, and here it's 24. And also the global symmetry has enhanced from U6 to SU5 times SU2 squared over here. And you can see it with the Dynkin diagrams in the quiver. And these differences, 24 to 20 and symmetries, they are the contribution of these massless instantons. And this is a very straightforward way to compute them. Now to conclude, well, before concluding, a last example to tell you, okay, sometimes there can be some problems. It was very important here that the level was specified to 0. There is a Chern-Simons level. If you change this to 1, then the polygon seems to have a problem. It's non-convex. So everything seems to break down. You cannot define a toric variety out of this. The brain web thing doesn't seem to work because you see these brains, they want to collide. If you try to go to the SCFT point, it doesn't work. And so it seems that you're stuck. Well, actually, you're not. From the brain web perspective, there is a way out. It's to do, you can use the monodromies that arise from the 7 brains. And then by brain manipulation and doing some kind of generalized Hanani-Witten moves, you can obtain a brain web that you can collapse. And then you have these tropical curves again. So here you have the blue one, the red one. And if you compute this intersection, you find a quiver like this. And then once you're here, you're safe because you have the magnetic quiver. So you can compute everything. You can compute the dimension, global symmetry, or anything that you like. This formally, we can write as a polygon, which is now convex, but it has this funny white dot over here because of this boundary condition on the brain web. So there's a big question. Is it possible to still do this way? Well, the answer is actually yes, and this is a work in progress, which needs an extension of toric geometry, or actually a breaking of toric geometry. So this Y here, this Y tilde, will not be a toric space. It will be a deformation. And actually with Andres Colinucci and Sakura, Stefanemeki, and Henrik Suss, we are working on 2 different approaches to understand this, one from tachyon condensation matrices and one from Minkowski decomposition and Altman's work on deformations of toric singularities. And the bottom line is that we can understand this. And well, I didn't show this example because it's complicated, but here is a simpler example. If you take C3 mod Zn squared, so here's the case for n equal to 3, and you add a deformation like this, then the equation is deformed by a space, by some monomial which breaks part of the toricity. And this story is actually more general, and this is work in progress that should appear pretty soon. And it's very exciting because it's a extension, quite a broad extension of toric techniques. So with this, I will now conclude. So we saw as a summary that magnetic quivers are a way of defining conical symplectic singularities. We can do this for many interesting spaces. I showed some examples. Some other examples that we worked out, in particular with Andrew Dancer and Francis Kirwan, are hyperKahler implosion spaces. You can also provide magnetic quivers for that. And the point is that once you get this description, you can do a lot of things, and you can compute data like dimension, global symmetry, the structure of the coordinate ring, the singular stratification, and so on. And for physics, this is particularly interesting because this singular stratification corresponds to the phase structure. And it also, I didn't describe this in this talk, but we can also use these quivers to understand how the theories are connected via RG flow, for instance. So a list of future directions and open problems. What is the scope of this? Can you describe every symplectic singularity with magnetic quivers? The answer is probably no, or rather it depends on what is your definition. You can extend the definition in various ways. I've only presented here the simplest objects, but there is a question of what is the most generic magnetic object. And then what other informations can be extracted from magnetic quiver? Can you say anything about the hyperKahler metric, for instance? And finally, is there a possible bootstrap approach, like bottom-up approach? And for this, of course, you would need the classification of all possible elementary slices. And as I said, it's an open problem. And there were actually a new development, the first one in 20 years, which appeared, I think, last month by this team of mathematicians. And immediately after, we found that this is actually appearing in Higgs branches of 6D n equal 1, 0 SCFTs, and we have magnetic quivers for that. So this is a ongoing work with Julius Grimminger and Daniel Juteau and Paul Levy. And the main question is, how do these slices combine in general from this atom? How do you form the molecules? So on this, I thank you for your attention. If you have any questions.
Thanks for the beautiful talk. And we have one question from Nikita.
Can you hear me? Yes. Very interesting talk. Very nice question. If I take your magnetic quiver and try to consider gauge theory, quiver gauge theory based on that, what's the relevance of that theory to the superconformal field theory you started with?
So yes, that's a good question. So in simple cases, it can be understood as the compactification of the, as the 3D mirror of the compactification to 3D. So in most cases, this would work, at least when it's simply laced and everything, because if it's non-simply laced, you cannot really define it.
But so in this case, in your example of SU3 with 6 flavors, if I compactify that theory to 3 dimensions, yes.
Yeah.
So you say that the theory based on that quiver would be the mirror?
Yeah, so if you start from, for instance, SU3 with 6 flavors in 4D, then you will get not that quiver, you will get that singularity. So there is another magnetic quiver for that. But if you start from 5D and you really go to the superconformal point.
Yes, I understand. So yeah. Okay.
So you should get this, yes. And then actually, I didn't really say, but how we derive some of the 4D quivers, sometimes you need to do twisted compactifications. And then it's when you do this twisted compactification that you get this non-simply laced quiver, for instance.
But it's something bothering me. So if I look at the Coulomb branch of that theory, so compactify from 5D to 3D on 2 torus, so that's going to be some modular space of SU2 monopoles on T2 cross R, I think, with some Dirac singularities. So I could take that, the fact that that's also a quotient of some infinite-dimensional hyperKahler quotient, so that could give me a description of mirror theory, but it doesn't look like that's what you get.
Okay, so I didn't explore this approach, so I don't know. Maybe we could compare then. If you say it gives something different, it would be interesting to understand. Okay, I don't know.
There's one more question here.
Thank you for your talk. Does magnetic quiver help you to guess what is the symplectic dual?
Well, yes. So yeah, very good question. So yeah, there is a kind of a general notion. The symplectic dual should be obtained, at least the diagram should be obtained by just taking the diagram. Let's take this one, and then you invert it, and you change all lowercase letter into uppercase letters, and then that should be the symplectic dual. So when you get the magnetic quiver, because you can obtain the diagram, in a way you have this description. It doesn't mean that you have a description, you don't have a magnetic quiver for the symplectic dual, but at least you know things like the dimensions and symmetries and all these things. So yeah, this we could, I can show you more about that.
I have one question. Can you say a bit more about this new development you mentioned at the very end? So there is some additional elementary slice, which is not in the list coming from the Affine Grassmannian.
Right. Yeah, that's right. So in this work here, so actually in the original work by Beauville, he asked, he already knew that there was the Klein singularities and the nilpotent orbits. And I guess Affine Grassmannian was maybe a bit understood at the time, but then he asked, okay, are there other things, in particular singularities which are not quotients of anything? So they are known as those with trivial fundamental group. And this was an open question since the beginning. And so in this work, they provide a new such singularity, which is actually low dimension. It's 4-dimensional. So it's quite simple, and yeah, it's just a new thing.
But they don't claim that's the end of the story. It's just one additional.
It's not the end. No, of course, it's not the end, and it's still conjecture that the list is it's not even known that if it's finite or not. So it could be an infinite list. So this is very, very difficult to see. But what was interesting here is that they found this new slice, and a month later we saw it in 6D physics. So maybe there is more to be discovered there. Well, probably there is more.
Okay. I don't see any further questions. So let's thank again Antoine.